So I'll be discussing the project I did on modeling bird populations on a small island. So I'll be introducing the inhabitants of Rangatira Island. So I can zoom in. Yeah, so these are the cute birds that the project was modeling. So they live on Rangatira Island, which is a small island off the coast of New Zealand. It's about a 2 kilometre by 2 kilometre island. And the island's separated into 2 distinct regions. So there's Woolshed Bush, which is a fertile region lower down, closer to sea level, and Tot Bush, which has got harsher conditions. And ironically, Tot Bush is at the bottom of the picture. And because it's got harsher conditions, it's got lower population sizes, so it will also be at the bottom of all the other diagrams throughout the poster. And the goal of the project was to model the population of female birds, female since it simplifies the problem slightly, using a 2-type population size dependent branching process. So the 2 types referring to denoting whether the bird is in Woolshed Bush or Tot Bush, in which region it is in, and the population size dependence, coming from the fact that since it's a small island and resources are limited, therefore, rather than the population growing exponentially, as it would without any bounds, it would exhibit a logistic growth where after initially growing exponentially, it would slow down when it reached a boundary of the number of resources, or in this case, nesting spaces that are available. And the specific type of model I worked with was a discrete time model. And what this means is that it looks at intervals of, in this case, the year. And over the year, if you've got X birds in Tot Bush and Y birds in Woolshed Bush, over the year, these birds would independently reproduce according to a particular offspring distribution. And the sum of all those of the new birds that are born will be the population size that is for the following year. And so this discrete time model allowed for the specification of a few different events that are happening in the birds' lives. So, for example, their death, their attempt to find a nest, their birth, and also the dispersal between the 2 regions, which is also another focus. How do the birds move between the 2 regions? And that's quite important in the model. So I'll briefly explain the kind of offspring distribution, which is the most creative part of the project, as I got to design essentially a mechanism, most realistic mechanism for how these birds might make decisions about their lives. Initially, the deaths were taken into account. And after that, if the bird would survive, then it would try to find a nest. So if successful, it would give birth to B offspring. And therefore, like the total offspring will be the B births plus the bird itself. The bird itself is included in the offspring. But if it's unsuccessful, then it gets to make a choice. Does it stay in the same region where it started? So if it started in Tot Bush, does it stay there? Or does it try and disperse to the other region, have another crack at reproduction? And so if it does that, then it would have a penalty because it's harder to establish new territory, biologically speaking. And therefore, there's another parameter, D, that is introduced as the penalty. It's harder to reproduce when you're in unfamiliar territory. And the population size dependence of the model, so it's one of the crucial features that enabled the populations not in the model to not skyrocket. Since the nesting space that was available is the limiting resource, the most limiting resource in this case, then it made sense for the R1 and R2, which are the probabilities of finding a nest, for them to be population size dependent. And there are a couple of different ways to structure this. So in the project, I considered 2 different types of models. So over here. So there's the Beverton Holt and the Ricker model. Both of these are essentially decreasing functions. So as the population sizes increase, the probability of finding a nest naturally decreases because more of the space is filled up. And so this introduced a couple of parameters, C1 and C2, which determine this population size dependence, but also the probability of dispersal between the 2 regions, M, was also something that there wasn't exact concrete evidence on at the moment, so it's another parameter to be estimated. But luckily, my supervisor, Sophie, had estimates for a few of the other quantities, for example, the distribution of births and probability of death, and there was also information found about how difficult it is to transfer or to disperse into new territory. So some of the parameters were already able to be estimated from other data, leaving only 3 parameters. One of the key quantities in this sort of biological example is to be able to find the carrying capacity of the island or of the 2 regions. That means that the population size about which the populations will stabilize, essentially. So about which the populations will oscillate around. And mathematically speaking, that's the same as thinking about the expected value of the population. So if your populations are X and Y, the carrying capacity will be the size where the expected value of your populations next year is the same as it is this year. So essentially, on average, you'd expect a stable population. And this can be since the distribution, the flow chart that you saw up there was consisting of rather simple Bernoulli and binomial distributions. This can be calculated quite simply and can be solved numerically for the carrying capacity. So the way that the populations look up here, this is a simulation of with a given set of parameters C1, C2, and M, where so you can see that initially on the diagram on the left, the populations seem to start to grow exponentially, but then they slow down and start oscillating around this carrying capacity value. And over a long period of time, so the Y graph goes up to many, many years, 5,000 years, shows that the populations will just, according to the model, oscillate for a very, very long time until you have a moment of stochastic misfortune where the oscillations just go down to 0 and the population becomes extinct. That's the general structure of the model, how it works. And the next task, perhaps the most interesting one, was finding parameter estimates. As to our knowledge, this hadn't been done for this particular type of model, specifically finding parameter estimates. So it's one of these nice problems where you don't know if it can be done, but you just have to try a few different methods and perhaps something will result. So a couple of ideas that were explored here was using maximum likelihood estimation, which is in essence, what is finding the set of values of the parameters M, C1, and C2 that will make the probability of the data that you see the most likely. So if you've got collected data from the island, you want to find values that will maximize the probability of that happening. And so mathematically, since the populations are determined by how many birds how many offspring each bird has, and there are X birds from one region, Y birds from another region. So to determine the next year's population, you'd be having the sum of all those offspring distributions. So therefore, the central limit theorem can come into play in one method. Also, probability generating functions were another common method that was also able to be in some way applied to this example. And apart from maximum likelihood estimation, also least squares estimation was looked at, and this proved to be the most computationally practical one of those. And what this is it's a way of minimizing the difference between, so let's say populations X and Y this year, minimizing the difference between what was expected from the model, the expected population size from the model in the following year, the difference between that and the actual ones observed in the data. And the maximum likelihood estimations were computationally quite challenging, and so there's definitely room for improvement for that. But luckily, the least squares estimation produced some viable result. And this is the point where we were lucky enough to have access to 20 years of data collected during different periods of the bird's life on the island. So it's the first 16 years, I believe, after the birds were introduced to the island. There were only 2 of them at the beginning, and the population has grown since then, and then another 5-year period later on. And so the diagram shows the expected population size. To notice they're more like equilibrium equations rather than the oscillating things seen in the simulations. And these are so the lines show the estimates for parameter estimates and estimates of the carrying capacity for the Beaverton, Holt, and the Ricker models. The 2 models, Beaverton, Holt on the left, Ricker is on the right, and for different estimation methods, maximum likelihood and least squares. So there's different types of estimates show a slight bias in a positive or a negative direction, but overall, it the estimates seem to be reasonable given the results. And remember how the populations are stochastic models, the populations oscillate, so it's not necessary that the lines actually go through the exact population sizes observed. Also, the shaded areas in the background is a 60% prediction interval, which was constructed using a bunch of simulations, 1,000 in fact, simulations of trajectories using the estimated parameters, and looking at the inner 60% area. So technically, 60% of the observed data points should be within those bounds. So the blue bound for Woolshed bush and the orange pink band for top bush. Yes, and so as a result, it was found that a model, a two-type discrete time population size dependent branching process model for this situation is viable. It does produce reasonable estimates for the carrying capacity, although it's hard to know for sure because it needs to be comparisons between the different types of estimates that I've gotten here, comparison perhaps between different types of model to see which one's more appropriate. But overall, this seems to be effective. One issue that might be visible is that in the estimates for the parameters themselves, the carrying capacities, but the probability of dispersal between the regions, that can differ quite significantly between the two different types of estimation techniques. And so that's an indication that with different values of C1, C2, and M, you can actually get quite different, quite similar, carrying estimates for the carrying capacity. So it might be that the model is not very good for estimating those values themselves. So it might not give up much information about the probability of dispersal. However, it still is useful for predicting the carrying capacities, K1 and K2, the two regions. And so as a result, this left me with a few interesting thoughts about where next to this model, how to make it more complex, how to make it a bit more realistic. So it seems from the data that the way that the birds disperse, often it is done straight after giving birth, so within the first year of giving birth, for just a lack of space. If your parents were in that region, they still occupy that territory. But also, interestingly enough, it's to it could be an ecological mechanism to increase genetic diversity, because if you stay in the same area, there's more of a chance that you as a bird might mate with a close genetic relative. So perhaps extending this dispersal timing to include it straight after birth or in different regions. So in other words, changing the flow diagram to make it a little bit more realistic or appropriate to the scenario. And overall, so this model is not necessarily specific to the island, although it was designed that way. If there's information about how the population gives birth, when it might migrate between regions, when it dies, it's going to be applied to any sort of closed population. In other words, ones where you don't get much migration away, because that will be hard to monitor. And so going off just the population sizes of different regions, it's possible to construct a model for how you predict population size will rise to the carrying capacity. Awesome. So throughout the project, I had plenty of help from my supervisor, Dr. Sophie Orphen. Also worked with Charles Breen. He was working on a similar project, but in a continuous time. So that's where instead of looking at yearly intervals, you look at essentially a continuous. You model it as if the bird population is changing continuously, which is actually what's more appropriately going on. Yeah, there were different results, but both of the models ended up providing some insight. So yeah, that's the presentation.